Okay. In this one, you can have duplicates. So duplicates values will be available, will will be present, and in this one you need to tell me the count of number of times a value existed. You can ignore the like you can ignore few of the functionalities of these two lines. These are the new conditions that is given to you now.
Okay, this sounds fun. So this time we'll use Tushar's way of doing stuff. So
I hope the question is clear to you.
yeah, so the new conditions are duplicates are going to be present, and we have to find the number of times that value existed. So basically, is there a chance that that value did not exist at all?
Yeah, let's keep that case as well.
Okay. So, so I'll use a binary search, but there are like going to be two types of binary search. I'll be
Okay.
looking at binary search. If I actually find the value, I'll look at the leftmost time, leftmost index at which that value was present. Then the rightmost point at which the value was present.
Okay.
And if I find both of them, it's like after that it's cakewalk.
Can you explain that to me again a little bit?
Yeah. So for example, we have 16. Okay. One thing I actually missed in this. Uh, okay. No, no. I thought I missed that. Okay. 7, 7. So this is still a valid
Um,
matrix, right?
you have changed the length. Yeah, now it's still a valid matrix.
Okay. So for example, we are trying to find 7.
Yes, you need to return me 3 as like the number of times 7 exists.
Yeah.
And in
So
case if an element is not there, just return 0.
yeah. Okay. So 7 is there, and there are three sevens. Let's just pretend that this 10 was not there and there was 121. No,
Mhm.
not this. Sorry. There's 7 over here.
Yeah, yeah, that's a better example.
Yeah. So in this, you have to get 7 at 4 times, right?
That's true.
So what I would do is I'll try to find the first occurrence of 7 and the last occurrence of 7. So
Okay.
how do I do that? So in a binary search, in this binary search, what we were doing was we were looking at the midpoint, and if the midpoint was the value, then what we would return is the index at that midpoint, right?
Mm-hmm.
So what if we actually found it at the midpoint, but what if we want to find out the leftmost as in the starting index at which this value is going to occur? So in that,
Okay.
what choices we make is that when we actually the midpoint actually reaches the uh, value, what we will do is we will actually record that at this index we found that value. But what we can do is we'll look at the left side of it. Okay. So if I have to show you this, it will be like 1, 2, 3, 4, 5, 6, 6. Okay. So what if at one point I got the midpoint as this 6? Okay. Sorry, not this one. At this 6. Okay. At one point. At, at that point, what I will do is I'll record the last time I actually found that at this index was at this index. And then what I will do is I will continue the binary search.
Okay.
Okay. So next time it will be at 5 or 4. And then after some time it will reach another 6. Because we are not searching on the right side, we are only searching on the left side. Every time I find another 6, I will actually record the position at which that 6 was. And after the entire thing is done, I'll return the index at which the last time I found 6.
Okay. But in this one, we are actually looking for the count.
Yeah. So this is the starting position. I'll do the same thing for in the reverse. So
So,
basically, I'll. Hmm?
but in like binary search, the usual decision that we make is based on the pivot, right? If the
Yeah.
value mid is equal to or less than equal, we take certain pivots. So,
Yeah.
in a case that you land on this one first, you will
Yeah.
still be making the decision to go on left and right in this parsing, right?
Uh, no, it depends. Like if I want to find out the starting point, I'll have to go to the left. If I want to find out the ending point, I'll have to pivot to the right.
Okay, so I got that approach. Just one doubt I have. So let's say that you do go to the starting point, right? Uh,
Yeah.
from there, are you saying that you will linearly count the number of times this is it?
No, no, I'm using two binary search. First binary search to find out the starting point. The second binary search to find out the ending point.
Got it. Okay. Sure.
So that will be log of m times n plus log of m times n, which is 2 log m times n, which is still log m times n.
Got it. Okay.
So there are binary search left and binary search right. And this time we'll actually use Tushar's suggestion. Uh, so binary search left, what we will do is value of it is value, then
Mhm. This one, instead of returning the value, Gotham is
so just putting a case of last occurrence is -1. Okay. That was not how it was. Sorry, page on the wrong place. Okay. We'll be sending the last occurrence. So binary left, binary search left, that will be the left, like the leftmost, the starting position. I think I should actually, yeah, left should be good enough.
you mean by left should be good enough?
No, the variable name.
Mm-hmm. There's a possibility that
Hmm.
line 39,
Yeah,
that first hit that you get on mid is the first occurrence of
yeah.
the setting end as,
Hmm.
and you are
So
storing the last occurrence. In that specific case, the end value will become out of bound in line number 30.
yeah, yeah.
Got it.
So every time I find the occurrence, I'll just store it, and then I'll just continue going on till I can find the last one.
Okay. So in these two ones, we will be getting the starting and the ending values. Now I'm really curious that you do have the start and the end of it. How are you proceeding?
So basically, I have some to do here. I'll just use a function, just as a function to uh, make it.
Does this function do value?
So it basically looks at the index and then gives this thing. What do you call that? See, it's basically a converter. It's an adapter for an array to, sorry, a matrix to an array and like that. The total length is like that. So so this is basically an adapter. So I'm just roughly writing it down. So row length and then x comma y is index by row length comma index modulus row length and return the matrix of x comma y. So basically you will just pass this over here. I'm just cleaning up the code. That's all. Yeah, yeah. I think this should oops, sorry, I actually forgot to write the solution. So yeah. So start equal to primary source left of matrix comma value. So if start is say is -1, start itself is -1, I can return 0, else end is binary search right matrix value, then return n minus star plus 1. I think this should work.
So I'm just like confused in the start and end values.
So where do you start? At which index is it starting? If it was flattened into a matrix, but what we are doing is we are adapting the matrix through a helper function like get value from matrix.
Huh?
So what if the matrix was flattened?
I think you mistakenly. Oh yeah, you pasted it. Got it. Yeah, if it's flattened.
If it's flattened, there would be an index at which this value is going to start, and there is a index at which the value is going to end.
Mm-hmm.
So I found out those two values, but I'm actually not flattening the matrix. It's just a
The
way, it's using an adapter pattern
yeah,
to actually make it work.
got it. Okay. Yeah, this code looks really modular.
Hmm.
Uh, what do you think is the time complexity you have in here?
It's a log of m times n, and the space complexity would also be O of 1.